Already, so this is not working. So I will try to work from computer here. So I will go all the way down. Yeah, all right. So I start from here. So I will this way for a while. I didn't print anything. So I will just second chapter 9 slide, the first slide. Oh, it's coming. So let's wait for a while. Yeah. Here we go. Yeah. All right. All right. So here it is. So look that compound. So I'm not going to draw that structure. I just want to draw this one, and I will explain this one. Yeah. N H H like this, and CH2. So you will expect one question from this one in the final. So I just explain from here. So C O, and you have OH here, O, and then you have H here, 2. Now, what are the hybridization in this in the central atom of this compound? So here, this is I think there is one double bond here, only one lone pair here. So look here. So how many wave projections for this one? 1 way, 2 way, 3 way, 4 way. So this is 1 way, 4 way projection. If you see the 4 way projection, that is definitely sp3 hybridized. So here is sp3 hybridized. Why? Because sp3, we have sp3, 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 sp3. So we have 4 sp3 hybrid orbital like that. And this is 1 sp3, this is 1 sp3, this is 1 sp3. So this is sp3 hybridized. So nitrogen is sp3 hybridized because it is 4-way connected. Make sense? And what would be the bond angle here? So you would expect 109.5, 109.5, 109.5, 109.5. But you would get a little bit less than 109.5 here, the bond angle. Why? Because this is one pair, so this is pushing this a little down, this is a little down. So I put that in the exam 3, if you remember that, NF3. Make sense? So this is a 4-way connection is sp3. Now let's look what is the hybridization in this central atom. So this is 1 way, another way, another way, another 4-way connection. So 4-way connection is sp3. It's impossible to be other thing than sp3. Make sense? Everybody got that? Now let's look here. So this carbon, how many ways this is connected? So this is 1 way, this is another way, this is another way. 3-way connection. So 3-way connection is always sp2. So we have only 3 sp2, 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 sp2. So this one is this way is sp2, this way is sp2, this way is sp2, this way is sp2. And this double bond is coming from the sidewise overlap of p orbital, which is unhybridized. Yeah. So how about this oxygen? Let's look oxygen. So what is the hybridization in this oxygen here? So this is 1 way, another lone pair, 2 way, this is 1 pair, 3rd way, this is 4-way. So we have 4-way bond around or electron pair around oxygen. So this is definitely sp3. Again, you would expect 109.5, 109.5, 109.5, but it is less than 109.5 here. Why? Because there are 2 lone pair and they push this bond pair toward close, and maybe it's about 104.5. Yeah, everybody got that? It's that simple. Hybridization is not that hard. Yeah, how it comes from the mathematics, I don't know, but just to memorize and take exam, it's not hard. Everybody got that? Good. So so now let's go here, and so now let's look one thing. So I just talked about sp3 and sp2 hybridized. We are looking at now. If you see something like this, let's say C let's say CN here, CH here, H here, H here, and let's say you look something like this. Now, what is the hybridization in this one? So you look here, so one way, two way, three way. So this is sp3 hybridized, yeah? And sp3 hybridized, four-way projection means 109.5 if there is no lone pair in the central atom, yeah? So there is no lone pair in the central atom, so bone angle is all 109.5, and hybridization in C is sp3. sp3 hybridized this guy. So how about this guy? Now let's look at 1, 2, 3, 4. But they are just two-way projection. So this is this way projecting, this is this way projecting. Only two-way projection. The two-way projection is sp, not sp2. If it is sp3, three-way projection. If sp3, four-way projection. Everybody got that? So if sp2, there are three, so there are three-way projection, like 1, 2, three-way projection. If this is sp3, four-way projection. So sp3, sp3, sp3. Now, if this is a two-way projection here, one-way, two-way projection, that is sp. So this guy is sp hybridized. This guy is also sp hybridized. Everybody got that? So two-way projection is if molecule is like this and there are no lone pairs, sp hybridized. Three-way, so two and one is coming this way. Everybody got that? So that's all about the hybridization. Yeah. So sp3 try to give you 109.5, but if there are lone pair at the central atom, a little bit less than 109.5, yeah, like 107, maybe 108, maybe 104, right? Something like that. And if this is sp2 hybridized, three-way projection, always 120 if there are no central atom, if there are no lone pair in the central atom, right? So if there is a lone pair in the central atom, that's not a three-way projection, that immediately becomes the four-way projection, right? So I'm saying like this one. So let's say B, F, F, F. So I have like this, one-way, two-way, three-way projection. So three-way projection is always this B is sp2 hybridized, three-way projection. If there are one lone pair here, what is the hybridization here? It will be like this, one-way, two-way, three-way, four-way projection. That will be sp3. Make sense? So like that. So if possible, I borrow here. So this is sp2. So the angle will be 120 here. And if it is a two-way projection like this, then you will get one-way, two-way projection. So this is sp hybridized. This is also sp hybridized. But if it was like this, like this, so this carbon is how many way projection? One way there, two-way, three-way projection. This is sp2. This is also three-way sp2. And I told you the double bond are coming from the unhybridized p orbital overlap in last class. Yeah. So like that. So I think we are done here. So let's go to the so everything is I wrote here, whatever I write here is the same thing. So angle 1 will be 109.5. Why? Because this is sp3 hybridized. This one angle you would expect 109.5. Why? Because one way, two way, three way, four way is sp3 hybridized, but it's a little bit smaller than 109.5 because of this lone pair here. Yeah. Here you see this carbon one way, two way, three way. So it is three way, and that is sp2 hybridized. So 120, 120, 120. So this one is one way, two way, three way, four way. So oxygen is four way oxygen alone electron pair. So this sp3 hybridized. Everybody got that? That's easy. Now let's go to look another one. So this is a molecular orbital theory. So again, this is coming from complex mathematics. So I don't know the math, so I will just tell you what the result of this molecular orbital theory. So this is the hybridization theory. Now, molecular orbital theory. The atomic orbitals are treated like waves that constructively or destructively act to form the molecular orbital. The electrons of the molecule are distributed over the entire molecule as a whole and explain the paramagnetism and of an atomic spectra of the molecule. So we'll talk about this one here. So like this. So let's look here. So although like the hydrogen, so let's talk two hydrogen. So you have one hydrogen here, you have another hydrogen here. So you have two hydrogen. Now this hydrogen has one orbital, we call S1s orbital, and that is like this one, the spherical. And this another hydrogen, it has one orbital like the one is orbital. So this one is orbital, one is orbital. Now these two guys want to bond. So what they say is that, so this guy is waving like this, and this guy is just like the water wave, yeah, just like the water wave, and this is also waving like this, yeah. So it's just like the water going up, water going down, water going up, right? So both of these orbital are waving. Now what happens is like this. So sometimes this guy and this guy overlap like this way. You see that? Peak to peak, peak to peak. So they overlap one to another. So that's very good, yeah? So these two waves are overlapping one over another, where peak is overlapping with the another peak, yeah? So this is good. Now, sometimes these are not overlapping this way, they are overlapping this way. So this is from there, and another guy from here, like this. So you look here, this is distributed. This is kind of this is going up, this is going down. So going up and going down are canceling each other. So this is called constructive interference. This is called destructive interference. So when hydrogen is alone, it is like this, and it is waving like this. Again, I don't know if that's true or not. Yeah, I just understand that way. So this one is waving like this, and when these two waves come together, just like the water wave in the river. So if two waves come peak to peak, peak to peak, you get a very big peak of the water, right? And if one wave is coming like this, another is going like this, and up and down just cancel each other. So this is called constructive interference. This is called constructive interference. This is called destructive interference. So if this is happening, the two hydrogen atoms try to stay together. But if this happens, the hydrogen atom try to break and want to be alone. Make sense? You got it? So if you get some condition like this, so this gives the stability. So like this one. So let's say, so you have hydrogen here, you have hydrogen here, and these two guys. So let's say you want to represent the one is orbital of hydrogen like this. One is orbital of hydrogen is this one, and they are in the same energy level here. So hydrogen has one electron here. Hydrogen has one electron here. Now I will tell you this orbital. So this line. So this line is the one is orbital, which is basically the spherical one. And this guy and this guy are constructively interfering and giving like this. And this guy is destructively interfering and giving orbital like this. So this is called atomic orbital. This is called atomic orbital. This is called molecular orbital. This is also called molecular orbital. And this is called bonding orbital because they are constructively interfering here, peak to peak, peak to peak. The upper one is called destructively interfere because peak is cancelled by down going peak, and upgoing peak is cancelled by down going peak. Make sense? So like that. So this is destabilizing the molecule. So hydrogen don't want to stay together if this is dominating in that condition. Yeah. So the hydrogen atom want to sit together if something like this is happening while they interact. Yeah. So let's connect this one. So like this. So look here. So this one, this one, this one, this one. So this is called atomic orbital. AO, atomic orbital of hydrogen. This is called atomic orbital of hydrogen. Now these two orbital, this orbital and this orbital combine, and they give the molecular orbital. So this is called molecular orbital. Make sense? So what is molecular orbital? This condition is called molecular orbital. So this, when they are alone, they are called atomic orbital. Make sense? So now this electron should be distributed when they are mixed, and they give something like this, and they should be distributed among these molecular orbitals. So one orbital can have maximum 2 electrons. So this electron comes here and sit here. This electron comes here and sit here like this. So there are no more electrons. 1, 2. So both electrons come and sit here. Make sense? Now let's talk about this one. So this atomic orbital of hydrogen, this atomic orbital of another hydrogen. So basically they mix together and they give constructive interference and destructive interference. And constructive interference is denoted like this, and destructive interference is denoted like this. And we have 2 electrons. So this orbital can have both electrons here. So now let's calculate how many bonds are formed between hydrogen and hydrogen. So you can say bond order, B-O-N-D, bond order. How many bonds are formed between hydrogen and hydrogen? So we said number of electron in bonding orbital, bonding molecular orbital minus number of electron in anti-bonding orbital. Number of electron in anti-bonding molecular orbital, and you divide by 2. So this is called bonding molecular orbital. This is bonding because this condition try to keep hydrogen and hydrogen together. This condition try to destroy that condition. Hydrogen and hydrogen don't want to stay together. Yeah. So let's look here. So number of electron in bonding orbital. How many? Bonding molecular orbital. 2 here, right? 2. And then how many electron in anti-bonding orbital? 0. So minus 0 divided by 2. 2 minus 0 is 2. 2 by 2 is 1. So hydrogen, and there is only one bond between hydrogen and hydrogen. Make sense? So it can predict how many bonds can form between 2 atoms of different elements. Everyone got that? You got it? Yeah, a little bit. Yeah. Now this is one prediction we can make. Now another prediction that guy was saying, we can talk about the molecular spectra of the atom. Molecule. So let's say hydrogen is in hydrogen molecule. 2 electrons are here. Now put in a cuvette, take a cuvette and put hydrogen molecule here, like in lab number 12. Yeah, in lab number 12, you did the molecular spectroscopy, right? So you put here, and this is hydrogen here, and send this light here from here. So when you send the light, the hydrogen atom this hydrogen molecule will absorb that light, and they give the shadow, which is called the observance in lab number 12, if you remember. Yeah. So how does that shadow come? So that shadow comes because when you give the light to this hydrogen molecule here, so that light comes here and strike this 2 electron, and the sum of the light is absorbed by this electron, and this electron is jumped here like this. So this guy jumped here. So because of that, light is absorbed some. That light, some of the amount of light is absorbed by that electron. So you got the shadow. Everyone got that? So this is called the molecular spectroscopy. Can be explained by this molecular orbital theory. Got it? So how does the shadow form in the, if you put, so in the lab number 12, you are putting something like this here, and you put the cobalt chloride, COCl6 cobalt chloride hexahydrate 6 H2O molecules dissolved in here, and it was a pink solution, and you are pink or red solution, and you are sending some light here, and when you get this way, you got 0.435 observance, meaning that the shadow of this solution is 0.435 and 99.6 is transmitted. So what gives this 0.435? What did absorb this light? So that light is basically you have a cobalt there. So you have a cobalt there, and the cobalt has something like this. So like that, like this, and there's a cobalt atom. This is another cobalt, and when this cobalt are sitting there or something like this, there are some electrons in this cobalt, and then when you give some light from here, so some of these electrons absorb that light and jump to the higher level here. So that absorption is 0.435. Everybody got that? So like that, or somebody get 0.34, 0.435, or something like that. Yeah. So this is called the spectroscopy, molecular spectroscopy in chemistry. So we are doing that in lab number 12. Yeah. Good. So like this one. So this is hydrogen. So 2 things we can predict from this theory. One is how many bond comes between 2 atoms, and some how much light is absorbed if we send some light from the solution of that material, which is called molecular spectroscopy. Observance, something like that. So we will be doing the same thing here. So let's do helium. Now I'm going to work with the helium. So helium is now look at the electronic configuration of helium. That is 1s2. This guy, right? 1s2. So look there. go to the chapter 7 and look what is the electronic configuration of helium. Hydrogen number 1, 1s1. Helium is number 2, 1s2, right? Yeah. So now let's try to bond helium and helium. So this is the helium 1s2. So this guy I'm talking about the helium. So I am going to represent that s orbital. So this orbital, this one is this sphere, but I'm going to draw that as a line here. Yeah. Yeah, so this is the 1s orbital, and then we have 2 electrons in that orbital. So I put like this way, and I put another helium atom here, and I put that orbital of another helium atom like this. And I told you 2 electrons for this one also, 1s2. Now this guy, this line, I'm not talking about the electron interfering. I'm talking about this wave. So this line, where I'm drawing this line is this guy, like waving like the wave. So one is waving like that. That hydrogen, this helium is also waving like that. So this guy. So I'm not going to draw there. So this is like this, and this is also like this. Now this one and this one constructively interfering here, and they are destructively interfering here, like this. Everybody got that? So I'm not going to draw this. So I just want to show you something like that. So this one is a constructively molecular orbital coming from constructively interfering, and this is coming from the destructively interfering. Yeah, and now so this guy and this guy mixing, giving this kind of system. This line is saying like that. Yeah. Now how many electrons I have now? 4 electrons. 1, 2, 3, 4. In one orbital, I can put only 2 electrons according to Hund's rule of maximum multiplicity, right? So you can put 2 electrons. I have 1, 2, 3, 4. So 4 electrons can be distributed everywhere in that molecule according to Hund's rules of maximum multiplicity. So I can put 2 here, and I cannot put more than 2. In one orbital, you cannot put more than 2 electrons if you go to chapter 7. Yeah. So and then 1, 2. 2 coming here, so we don't know which coming here. So are they coming here? Are they coming here? One coming from here. We don't know because we have those electrons and we throw everywhere, mixing there, and which coming there and which sitting there. We don't know. Make sense? So like that, and then 2 go and sit here. So we call this is a bonding molecular orbital. This we call is anti-bonding. So anti-bonding. So bonding try to bring helium and helium together. Anti-bonding try to separate the helium and helium far away. Make sense? So what kind of molecule forms? Let's predict the bond order in the helium. So now bond order, how many bond form? Bond order means how many bonds are found between helium and helium. So helium. Do you get 1 bond, or do you get something like this, or you don't get anything? So alone, or you don't have anything in between this one. So let's look here. So bond order is equals to half number of electron in bonding, number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital. So look here. So half number of electron in bonding orbital is 2. Number of electron in anti-bonding or molecular orbital is also 2. So 2 minus 2. So that is half 2 minus 2 is 0. So 0 multiplied by half is 0. So bond between helium and helium atom is 0. So helium and helium don't bond, they are the separate always. Everybody got that? In hydrogen, there was 1 bond between hydrogen and hydrogen, right? So there is, you never see in chemistry book, you never see something like this. Because helium and helium never come together and sit together. Why? Because the effect of bonding orbital is cancelled by effect of non-bonding orbital. Yeah, makes sense. The number of electron in anti-bonding is also 2. Number of electron in bonding is also 2. So 2 minus 2 divided by 2 is 0. Got it? Like this. Now let's go another one here. So this one was hydrogen. I already talked about this one. This is what is this one? This is excited state of hydrogen molecule. So let's talk about the excited state of hydrogen molecule. So excited state meaning that there is a hydrogen molecule excited state of hydrogen. Will it be stable or not stable? Two hydrogen atoms are sitting together or not together, not sitting together. So let's say, so normally hydrogen is like this. So if you take some hydrogen in test tube and you have not heated it and it just sit like this, and hydrogen is always, two hydrogen are always sitting together. So that is called the normal hydrogen or ground state hydrogen or normal state hydrogen. Make sense? Now let's put this hydrogen here. So let's take this hydrogen here and put in this test tube and give it a lot, hit this, keep hitting. All these are broken, bond are broken, and they separate like this, hydrogen and hydrogen. So how does this is explained here? So let's talk about that one. So what happened here is, so you have hydrogen here, you have another hydrogen here in excited state. So you have one s orbital, you have one electron here, one electron here, 1s1, right? Hydrogen is 1s1, right? Because hydrogen is 1s1. This is also 1s1. This is hydrogen atomic orbital, hydrogen atomic orbital. Now, what happened here is, it's like this. So this and this gives one bonding molecular orbital. Here they give another bonding molecular orbital. So like that. And what happens is, it has two electrons here. Now, what happened here is, in normal condition, both this electron and this electron come here and sit here. But if you give some energy to this molecule, so in hydrogen I draw like this, right? But if you give some energy, what happens is that some of this, one of these electrons jump to absorb some energy and go here. Yeah, make sense? Sure. I put a lot of question in exam 3 like this. So how much energy should absorb to go from down to up? Would it go to 2? Would it go to 3? Would it go to 4? Right? So I put a lot of question in exam 3. If you look there, so if it absorbs a small amount of energy, it cannot jump. If it absorbs the right amount of energy, it can jump from here to here. But if this guy jumps a lot of energy, just go out from the system. Make sense? So it just absorbs some of the energy from here to going from there to there. This is excited state. When you hit the hydrogen molecule, so this is hydrogen molecule, put it test tube, hit it by giving the energy, and then one of the electron of the molecular orbital jump to anti-bonding orbital. So this is bonding. This is bonding molecular orbital. This guy is anti-bonding. So now bond order will be half number of electron in bonding, that is 1, minus number of electron in anti-bonding, that is also 1. So 1 minus 1 is 0, half multiplied by 0 is 0. So excited state, two hydrogen atoms can sit together. They explain that way. Make sense? So basically electron absorb the energy, go up in the upper level, and that cancel the bonding state. Everybody got that? Good. So it's pretty simple actually. So now let's look so we just finished the hydrogen and helium, and what do we have now? Let's look another one here. So why does helium doesn't exist? I already told you, because you cannot get helium, because in bonding molecular orbital you have to. So these two guys are coming and sitting here in bonding molecular orbital. These guys are coming and sitting here in the bonding molecular orbital. So formula for calculating the bond order, bond order is 2 minus 2 divided by 2, which is 0. So 2 minus 2. So there is no bond between helium and helium, so you cannot get helium. Very unstable. Everybody got that? Easy, right? So, but I don't know where it's coming from. I think they say it's coming from some complex mathematics. That's true or not, I don't know, because I don't know that math. Yeah. So now let's look other kinds. So this let's look this one. So boron, carbon, and nitrogen. We have two systems. One is boron, carbon, and nitrogen. Another is one is boron, carbon, and nitrogen. Another is oxygen and fluorine. So we have two kind of systems. So this is one kind of they form one kind of molecular orbital. They form another kind of molecular orbital. So we need to do these two things. Yeah. So and then we just fill the electron and then we calculate. So if you let's say you look the nitrogen. So let's look take nitrogen. So let's draw the atomic orbital. 1s. So number what is the atomic number? The number is 7, right? So nitrogen. If you look at the periodic table, it is in number 7, right? So this is 7. So this is 1s2, 2s2, 2p, 3. So this is the nitrogen. So all right. So the carbon is also similar. 1s, 2s, 2p. So even if you don't write the electron now, 1s, 2s, 2p. So this is also 1s, 2s, 2p. This is also 1s, 2s, 2p. This is also 1s, 2s, 2p. So this is also 1s, 2s, 2p. This is also 1s, 2s, 2p. Yeah. So all look the electronic configuration in chapter 7. 7, right? So 1s, 2s, 2p. Good. So now let's look nitrogen and nitrogen. So nitrogen. So I put nitrogen here. So nitrogen. How many 2p in? How many? So this 1s we don't have to show because this is inner orbit. 1s doesn't take part in the. I mean, you can draw it, but we really don't have to show the inner orbit electron, inner orbit orbital. Make sense? So one is basically nitrogen is like this. So this is nitrogen. Nitrogen is 7. So this is neutron proton here. So 2 electron here. So 5 electron here. 1, 2, 3, 4, 5 electron here. And the second orbit is divided into 2 parts. So this one is 2s, another is kind of 2p. So we do like that. So this is the valence shell. We only consider valence shell. So you really don't have to work in the inner orbit, that 1s. Yeah. We only talk about the 2s, 2p. I mean, you can draw if you want, but we really don't want the inner orbit here in volume. Yeah. So let's talk about this one. So I'm not talking this one. So let's take another nitrogen here. So that's 1s, 2s, 2p. So again, I don't need this one. So 2s2, 2p3. So I only need this one. So let's make if you want to draw 2s also, that's fine. But even if you don't want 2s, because 2s, 2 and 2s2, they are cancelling each other, equal number there. So you also don't need 2s here. I only need 2p. Because 2s2 and 2, both 2s2 are same, right? So they will cancel later when we draw. But we can, I can show you later that one. So let's look 2p. So how many 2p are there? So although you see 2p1 here, so but this p is 3 shifts, px, py, pz, right? Px, py, pz, right? So this is 3 shifts. So 1 shift, 2 shift, 3 shifts. So in one nitrogen, px, py, pz, like that. So one is px, another is py, another is pz, like that. And this one is also px, py, z. They should be in the same line because they have same energy, like this. This is, you can write px, py, pz. Now they interact. So px and py constructively and destructively interfere, just like how I draw for the hydrogen and helium, right? So when they constructively and destructively interfere in boron, carbon, and nitrogen, they form like this. So 2 orbitals come here, then 1 orbital sit here, and then 2 orbitals go above this line, and then 1 orbital is right here. So they sit like this. So like that, yeah. So this means this dot means they are coming from here. Everybody got that? So when this 6, so 1, 2, 3 of this, and 1, 2, 3 of this constructively and destructively interfere and give 6. So 1, 2, 3, 4, 5, 6. 6 orbitals constructively and destructively interfere and give 1, 2, 3 constructively form and 1, 2, 3 destructively form. Make sense? Everybody got that? Just like it. From 6 comes 6, right? So here is the problem. So if you look the boron, carbon, and nitrogen, it looks like this. But if you look the oxygen and fluorine, this flip like this. So this guy comes here. Everybody got that? Don't ask me how it comes. I don't know how it comes. It comes like this way, yeah? Because that's how the experimental results show. And when theory people come and they just try to adjust with the experimental result by doing that way. If you put this, if they make this way, they can explain the experimental result. But if they put the oxygen and fluorine this way, they cannot explain the experimental result. Make sense? So boron, carbon and nitrogen, you must draw like this way. But for oxygen and fluorine, you must draw like this. Everybody got that? That's one is the difference. Now we need to fill the electron, and this class is over with that. Yeah. So let's fill the electron. So let's look the nitrogen first. So it's a boron or nitrogen. We can put anything here. So this is a nitrogen molecule. So if you look at the nitrogen, so nitrogen is number 7. So this is 2, 4, 3 electron are here, right? In nitrogen, 3 electron are here. Make sense? 1s2, 2s2, 2p3. Now this nitrogen also have 3 electrons like this. Now we need to distribute those 3 electrons in all these orbitals. So for nitrogen, so nitrogen is like this. So for nitrogen, boron and carbon, we need to draw like this one. Now we start to fill the electron one by one first. So this and this level is same. So how many electrons we have? 3 here, 3 here. So I have 6 electrons. So I need to put 6 electrons in the same energy level. I need to put one by one. So 1 here, 1 here, 1 by 1 in the same energy level, 1 by 1. And then you need to pair it there. So 2, 2. I pair there. Now another you need to put here. 5. Now do you have another electron? You need to fill this guy before to go to another energy level, like this. Everybody got that? Good? Like this. Now let's calculate the bone order in nitrogen. So bone order in nitrogen is, so this below this line are bonding molecular orbital. Below above this line is anti-bonding. Make sense? So let's talk. All are in bonding. So all are in bonding. So bonding number of electrons in bonding orbital is 2, 4, 6. Number of electrons in anti-bonding molecular orbital is 0. Right? Nothing. So 0. Then you have to divide by 2, and that's 6 by 2 is 3. So nitrogen. If you have a nitrogen molecule, they have 3 bonds like this. Everybody got that? Good. Now, how many electrons are here? Are there any electron on pair here? 1, 2, 3, 4, 5. Pair. All electrons are paired. So this is diamagnetic. It's not a paramagnetic. If you go back and look the chapter 7, what is a diamagnetic? Something that is pulled toward magnet is called diamagnetic. Something pushed by magnet is called paramagnetic, right? So if all electrons are paired, it is pushed by magnet. So this is diamagnetic. Nitrogen is diamagnetic. Make sense? So this guy is diamagnetic. Why nitrogen is diamagnetic? Diamagnetic meaning it's pushed by magnet, pushed away by magnet, pushed away by magnet. Why? Magnet. Why? Because all electrons are paired. P-A-I-R-E-D, paired. There is no unpaired electron. So if you put some nitrogen gas here, I'm not talking about nitrogen atom. I'm talking about N2 gas, N2 molecule. So put nitrogen here, hang with some thread here, put a very big magnet here, North Pole, South Pole. So this nitrogen gas is pushed away by that magnet. Make sense? That's how they explain. Yeah. So this is the highest knowledge people claim in the field of human civilization. Is that true? I don't know. Yeah. So it's like that. So now let's go here, and so let's talk about another. So you can just exactly do the same thing for carbon. So I just did for nitrogen here. So everything is same. Let's do it for carbon. I told you this is for boron, carbon, and nitrogen. Nitrogen, I just finished it. So let's take out the electron from here, and let's do for the boron. So boron. So same thing. So let's look the boron. So boron is how many number? Number 5. So hydrogen, helium, lithium, beryllium, boron 5. So that is 1s2, 2s2, 2p1, like that, right? 2, 4, 1, 5, right? Now again, you don't have to work on this one. You don't have to work on this one. So P is Px, Py, Pz. Another P is Px, Py, Pz. So how many electrons I have in boron? In boron here, another boron here. Well, just one electron. I have one electron. I put here somewhere. I put one somewhere here. So exactly this one. Look here. So this one electron comes first here. Another electron comes. So you cannot put, as long as there are shift in the same energy level, you cannot pair electrons. You need to put one by one first. That's called the Hund's rules of maximum multiplicity. Make sense? Now let's calculate the bond order. So bond order is number of electron in bonding molecular orbital below this one, 1, 2. So 2 minus number of electron above this level here, 1, 0, 0. Both are 0 there. So divided by 2. So 2 by 2 is 1. So 2 minus 0 is 2. 2 by 2 is 1. So boron and boron has only one bond between them. Make sense? Easy? Confused? Okay, right? Boron and boron is like this one. Is it a paramagnetic or diamagnetic? So if you take some boron molecule here, and you hang with the thread and put near big magnet, would it be pulled toward magnet or pushed away from the magnet? Pulled, because unpaired electron. So if this is a 2 unpaired electron, it behaves as a magnet, another magnet. Make sense? So this is paramagnetic. Everyone got that? Yeah, you will understand. Yeah. So like that. Now let's look. How much time we have here? Oh, we still have some time. Now let's look the carbon. So how many bonds will form between carbon and carbon? So I'm going to work with the carbon here. I didn't change everything is same here. I did not change anything. So I just changed and put the different number of electrons. So carbon is like this. So carbon is 6, 1s2, 2s2, 2p. How many? 6. So 2p2, right? Like this. This is carbon. Make sense? Carbon is number 6, right? So like that. So so I don't use this one. I don't use this one. I only use this one. So this although it looks like a p, it is 3 sets, px, py, and pz. So like that. And this is already px, py, pz, px, py, pz. How many electrons I have with the carbon? So that outside I have 2 electrons here. So I put 1 electron here. You can put anywhere. Here, doesn't matter. Just put somewhere, yeah? So 2 electrons there, 1 by 1. Put 1 by 1 here. Now you need to start to fill those electrons here. I have 1, 2, 3, 4. So I'm working with the carbon, C2. So 1 electron first from here at the bottom. You cannot put 2 electrons at the same time in the same energy level. You need to put 1 by 1 first, right? Now you put another here, 2. Now since they are not filled, you need to fill them. 4, like that. Now 1, 2, 3, 4. All 4 went there. I don't have more electron now, right? Now look here, above this level 0, down this level 4, right? So bonding. So carbon. So a bond order in carbon is, bond order in C2 is, bonding is 4, anti-bonding electron is 0, and then you divide by 2, 4 by 2 is 2. So if you look the carbon in carbon, this will be like this. Bond order is 2. Make sense? Everybody got that? Good. So like that. Now take C2. Let's take C2 molecule and put here in the test tube and hang in the ceiling here and put a big magnet, not the southward. Would it be pulled or it will be pushed? Look here. Pair, right? Both are pairs, so pushed away. Diamagnetic. Make sense? If there is a one unpaired electron, it is pulled. That's paramagnetic. If all electrons are paired, those molecules are pushed away by the magnet. Got it? So now let's look one more. So we just finished boron, carbon, and nitrogen. Now I'm going to look oxygen and fluorine. So for oxygen and fluorine, every other thing is same. What I told you, this guy should be put like this. So put like this. All other things same. Is it? I didn't change the other thing, right? I just put that down, up to down. Make sense? So let's look the one fluorine, and then you can practice other. And I think we still have one more class in 15. If you come, I need to come. I will come and I talk a little bit about the exam. And so let's talk about the fluorine. So what is fluorine? Fluorine is number 9. So that is 1s2, 2s2, 2p5. This is fluorine because 9, right? So 2p5. This is fluorine. Fluorine is 9 atomic number. Now this is one fluorine. This is another fluorine. So again, I am not going to work with this guy and this guy because they would cancel later. So I just want to this p5. Now start to put 5 electrons here in the atom. 1, 2, 3. First put 1 by 1 and then 4 4, 5. You put like that. And here also put one by one. This guy also has 5. 1, 2, 3. Now put 4, 5 like this. Doesn't matter how you put. But first you need to put one by one, and then you need to start pair. Make sense? Everyone got that? Now let's distribute the electron. So how many electrons I have? 5 here, 5 here. I have 10. So I start to put 1 here first. Do I have more electron? Of course I have 10. I just put 1. Now I make 2 here. I'm done here. I cannot put more than 2 electrons in one orbital. Now I'm going to put 1 here and 1 here. This is same energy level. Now I have still more electron left. 2, 4, I put 5, 6. Like that. So these all are filled. Now I need to put 1 here and 1 here. Now how many? 2, 4, 6, 7, 8 are 8 electrons are gone. Now I need to pair here 9, 10. So 10 electrons are gone now. Count it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 are there. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So number of electrons, all number of electron of those atomic orbitals come and sit in the molecular orbital, right? Everybody got that? Easy. Now let's count the bond order. If F and F bond, would it be FF or would it be FF or would it be FF or would it be no bond between F and F? Yeah. So we are just going to do that. So let's calculate the bond order. Bond order would be number of electrons in bonding. So below these are bonding. So 2, 4, 6. 6 minus number of electrons in anti-bonding. 2, 4. 4. And then we have to divide by 2. 6 minus 4 is 2. 2 by 2 is 1. So if fluorine and fluorine make bond, the fluorine and fluorine is 1 bond. Makes sense? F2 is always 1 bond. Everybody got it? So you for oxygen, I will how much time I have? So maybe you are hurry to go home, right? So I just want to. So it's okay. Now you can also calculate yourself for oxygen. Now would it be a paramagnetic fluorine molecule? If I put a lot of fluorine molecule here, would it be diamagnetic or paramagnetic? So look here. So it is pair, 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 pair. All electrons are paired. So it is diamagnetic. Make sense? Now let's fluorine oxygen. So I just finished the oxygen also. It's okay. We can do it in next class. You just fill the. I already drawn here. So electrons. You can go and look here. So fluorine and oxygen. I just finished. Is it a fluorine? No, it's oxygen. Previous was fluorine. Did I draw the fluorine? No. So this is oxygen. So fluorine I did it here. Yeah. Now oxygen look here. Oxygen look like this one. Now look the bond order. So 2, 4, 6 are bonding. 1, 2 are anti-bonding. 6 minus 2 is 4. 4 by 2 is 2. So oxygen is 2 bond. Between oxygen and oxygen is you will get this kind of bond. O double bond. Make sense? And is it attracted toward a magnet or it is repelled by the magnet? You can see here. Pair, pair, pair. Unpair, unpair. So you can see here unpaired electron. So it is attracted toward the magnet. It's a paramagnet. Everybody got that? It's pretty easy, right? But they say nobody can understand this concept. Very, very few understood long time ago, and only they knew it. All right. So thank you, everyone. So still we will meet in 15, and if you call, I will talk a little bit about exam in 16, and we will start. Good? Say again. Oh, we don't have class in 15. No. Oh, okay, that's fine then. So I will hold office hour tomorrow between 1 to 2. So you can just join if you have any problem. I already put homework and all exam 1 and exam 2, and you can just read. Homework and exam should be enough for final. Yeah. You know, we just yeah. So exam 3 was a little bit hard. People complain, so I tried to make a little bit easier. Let's see. Yeah. Can you email me? I will make it. Yeah. Yeah. Yeah, all day. Yeah, it's very hard because if I take tonight, it will log in the canvas crashes. Yeah, it's hard. So. Yes. That's great. Thank you very much. Yeah. I like teaching, you know. I like teaching. Yeah, I really like this. A lot of students or people say, oh, you can simplify the material. It's amazing. Yeah. Cool. Yeah. That's great. Yeah. Yeah. Yeah, you do.